Hello everyone, I am Dr. Belmont and this is going to be the first attempt for me to create a video so I can continue the content of my classes, right? And right now the idea of this lecture is to continue talking about ideal gases, okay? So let's try, let's move the screen to somewhere that we can actually write down. Very well. So let's try this app. This is the first time that I'm going to use it for this, so I don't know if it's going to work properly. And I'm going to choose my pen. And there you go. Let's see how this works. Okay. So what we were discussing last class was the concept of ideal gases. Okay. And ideal gases have the concept that they might be described as what? Well, if I put a box and I put a bunch of dots inside of the box, right, then I can tell that I have what? An ideal gas. So what I am actually doing is describing gases as what? As dots in space, literally. As if you have a cross, then this is a dot. That is what this model is going to tell us that the gas is, okay? So definitely is not the most accurate, right? Because we know that actually gases are made by molecules and molecules are not dots in space. But the thing is also that with the equation PV the same as nRT, right, we can have actually a good accuracy in terms of the things that we can predict with this model, okay? So although ideal gases are not what? Dots, right? With these, we can have a quite accurate prediction of how they are going to behave. Okay, very well. So in class, you might well remember that I talk about pressure. Okay, and pressure is the most important aspect of a gas because it's the easiest one to measure, technically speaking. And if I want to clear pressure, right, from this equation, what do I have to do? Oh, pretty simple. I will remain N RT, but I will divide this this term by the inverse of the volume. So right now what I am doing is creating pressure as what? As a direct inverse of volume. The same thing that we have already been discussed into class. But there's a technicality here that we have to observe, right? So let's count the variables that we have here. We have 1, we have 2, and we have 3. And there's a problem. There's a problem because we only have how many equations? Only one. So how do you think we are going to solve this problem? So I'm going to give you a couple of seconds to think about it, and I will give you the answer in a moment. Very well. Okay, so if you notice, we have to do something about it, right? Because I want to transform what? This P, the same as what? As times over V times something else, right? And I'm just going to say here times a full constant, something that doesn't change. Okay, this is a C constant, sorry. Let me erase this. I want a constant here. There you go, okay? So I can transform what? This symbol here of correlation to what? To a symbol of equality. And that is very simple. Actually, what I have to do is to perform an evaluation. Evaluation of what? Of pressure and as a function of volume. But now I need to keep my temperature as what? As a constant. Okay? Very well. So what does this mean? Let's use another page. And let's put this into a practical example. Okay? Imagine that you have a container. Here's my container. Okay, and in the container, what do I have? My gas. Very well. Remember that a container can also be what? A piston, right? Do you remember our pistons? Very well. That means that I can change specifically what? The volume, right? Because I want to create what? A pressure in terms of the inverse of the volume. So the question here is going to be pressure. How am I going to measure it? Well, I need to set my parameters according to P, V, and RT. Sorry, let me erase this. P be the same as nRT, right? I need to know what? The number of moles, the constant of gases, the temperature at which I am going to use, and the volume in which the gas is contained. So if they are asking for you to what? To measure the pressure of these, well, we need to set our parameters. The first parameter in which we are going to work is that N is going to be 1 mole. So we're going to keep things simple. R, you already know that is going to be 0.082 what? Liters, atmospheres over mole and Kelvin. And here comes the trick. The volume is going to be 0.75 liters. Okay, and the temperature is going to be 300 Kelvin. So what you see here, all of these conditions, right, are the ones that I have specifically to contain my gas in this piston. So what you see in this piston, right, is actually what? 1 mole of a gas, any gas, let's say for example oxygen, okay? The volume of this piston is going to be 0.75 liters and the temperature is going to be 300 Kelvin. So with these parameters, guess what? Now we might be able to measure what? The pressure. Well, not to measure, but to calculate the pressure. So I know that I have how many moles? 1. R is 0.082 liters, atmospheres over mole and Kelvin. And the temperature is going to be 300. What? Kelvins. There you go, kelvins. And this is going to be 1 mole. Very well. All over what? Well, the volume. And the volume is going to be 0.75 liters. Okay? Very well. So let's see what the dimensional analysis tells us. We have liters here, right? Well, we have liters also there. I also have what? Moles that will go with moles and kelvins that will go with Kelvin. So we end up with only atmosphere. So it's okay. Pressure are going to be measured in atmosphere. So the dimensional analysis tells us that we are actually doing the correct thing. In those terms, then the pressure is going to be how much? Well, only using numbers because I already performed the dimensional analysis. 1 times 0.082, right, times 300, and I'm going to get atmospheres, right, all over 0.75. I'm going to give you a moment so you can perform the math on that, and I'll be back in a second. Very well, so when you perform the math to do that, the number that I get is 31.8 atmospheres, right? So it's a lot of pressure, right? Imagine that what you have here in 0.75 liters, right? If you have inside what? 1 mole of oxygen, the pressure that you're going to get is 31.8 atmospheres. It's a lot. Why do you think is that? What do you think is that? What if I have, for example, my gas, 0.75 liters, and I have 1 mole of a gas? The pressure is so high. Well, the answer for that is that the volume is what? Really small. Remember that a mole is 6.022 times 10 to the 23 atoms or molecules, right, of whatever you are measuring. So imagine that you have this number inside this box, right, or piston, in this case our piston, in only how much? 0.75 liters. So the problem that we have here is that we have a lot of molecules inside in a very small space. So hence what you get is a very high pressure. Okay? So remember that when you have low volume, then what's going to happen is that the pressure is going to increase. So we have to do something about it, right? It's not safe to have oxygen, right? Because it can explode with so high pressure inside of the container. So we have to do something in order to make pressure go down. Okay, how do you think we're going to do that? Well, one way would be to increase the volume, right? But it would be redundant because we have already studied the system. No, we have to do something else. Let's think what we can do. And the other thing that we can do is to use the other variable that we have, and the other variable that we have is what? Temperature. Very well. So what do you think I can do with temperature, right? If I want to lower the pressure? Well, pretty simple. The only thing that I need to do is to lower the temperature. Very well. Let's see how that goes. So again, I'm going to have the same conditions. I'm going to have my piston of 0.75 liters. Okay, and I'm going to have still what? 1 mole of a gas. Excellent. But now I'm going to do some changes. And well, R, I know that is a constant, so it is not going to change. And what do you think I'm going to do with the temperature? Now I'm going to change it to 175 kelvins. Very well. So let's go and make the substitution here. I already know the dimensional analysis, so I don't have to waste time on that. And I know that I'm going to have 1 mole times 0.082, right? This is this number, very well. Times the temperature, which is going to be 175 kelvins, right? Well, dimensional analysis, there you go. We don't need it, we already know that we're on the right track. Over how much? 0.75. So I'm going to give you a moment so you can do the math. Very well. And when you finish, the resultant number is going to be 19.13 atmospheres. So you see there's a dramatically change in terms of the pressure. The same volume, but with a lowest pressure. Why? Because we decrease the temperature. Very well, I'm going to stop this video up to now, to this moment, and please let me know what you think. Please let me know if this is working, and if you have any other suggestions, please let me know. See you soon.